Hello. Hi, everybody. Good morning. Uh, Today, we are going to go over through uh, the fundamentals of machine learning and deep learning, and then we're also going to take a look at the tools that can actually leverage for implementation of what we are going through. But we're going to see like how critical it is for us to be able to have some prerequisites for getting into as a next generation consultants. You all will be joining universities and you'll be joining various higher education courses, and we're going to take a look at to see why and how it is critical for us to join all these courses, and what is that we need to have before we join these courses. It's very critical that you have some amount of linear algebra, and you also have some amount of calculus, which you'll be going through in your school anyway. But it's important to know like what are the fundamentals that we need to have. So it's important to have the linear algebra, calculus, and a few basic concepts of neural networks, and how we're going to build our own neural network. How do we activate a neuron inside of a neural network? And then there's a whole list of algorithms that are available for your consumption. Again, based on your career objective, if you want to go with Python or PyTorch or TensorFlow based on your choice of your programming language platforms. But before we even get into the programming, it's essential for us to have the background of the linear algebra and calculus as mathematical background. And that's what will help you to be able to implement all these algorithms on your own. So again, here there is a book that I put together for you guys that you want to go through, and it covers all the prerequisites of getting into machine learning and data science field that you are aspiring to get into. So you can go to the concepts of what are all the linear algebra, because you might have received several materials, ebooks, and books where people will just get into they start introducing the statistics, and then they will take you to the programs implementations. But again, it's not just the statistics that is important for you in terms of implementing a machine learning or a deep learning algorithm. It's also critical that you need to have a background of math, because when you're talking about algorithms, I'm pretty much covering all the statistics anyway there. But other than the statistics, right? For example, if you're going to implement an I-Bayes algorithm, or you're going to implement linear regression algorithm, or logistic regression algorithm, or you're going to implement a few of the other type of algorithms, right? So for you to launch your career, to be successful, to be a successful data scientist, that there are a few prerequisites that you need to have. Okay, I'm not highlighting statistics here, because when I'm saying algorithms, it's going to pretty much cover all the statistics behind each algorithm. And again, in this book, I illustrated it so clearly that you can go to each algorithm that you want to implement, and I'll give you a formula of statistics that you can go through, and you can understand, okay, here is a statistics background, here is the equation for it. Now I'll give you the math for that. And if at all, like we also require linear algebra, we need calculus for it. For example, if you want to implement stochastic gradient descent, or you want to implement back propagation algorithms in neural net with leverage of a neural network, then it is important for you to be able to understand what is the chain rule for implementing the stochastic gradient descent, or what is a particular algorithms or a math formula for you to apply linear algebra into a statistical algorithm, right? For that, I'll give you an example. And in fact, today we're going to go through all of the math, linear algebra, and calculus, both required for you to activate a sigmoid function, or you want to activate neural network. And then you're going to implement a stochastic gradient descent algorithm today based on gradients paper that was proposed a long time ago, so that you can take a look at that paper, and that will give you a clear understanding of how exactly you're going to be able to implement this algorithm for you. So let's take a look at the importance of the math and calculus for your implementations. Again, this is just a brief background of the types of projects that I worked on, and the type of algorithms and fields of machine learning and deep learning here. I'll give you just a brief background of all of those um, you know um, projects that you want to go through. But again, you can get this book at xlibris.com and for your implementation, and you can also come up with additional questions after this session that you were not able to go through in this session, and you can also connect on LinkedIn and send those questions. You can feel free to just DM me, and you can get your answers for any additional questions and clarifications. But we're going to try and cover everything today so that there will not be a lot of room for questions. So again, so as you are all, getting into the field of machine learning and deep learning, so it's very fundamental and important for us to understand, what was the history of machine learning or deep learning we have. And so there are a lot of, as you know, in 1940s, Alan Turing has proposed a paper that would, become the foundation for Turing machines and finding the artificial intelligence, because we want the machines to think the way humans do by the intuition rather than the rules. Because if you see the machine learning and machine intelligence and artificial intelligence that was built in 1980s, it's more like a rules-based system. So where the rules are like you're gonna like encode your system with millions of rules. In fact, so if A is B, execute something. If A is C, execute something else. So, but what if you're not hitting the scenario that you already planned for, and you're getting some scenario at runtime, which is like, for example, if you take autonomous vehicle with reinforcement learning, and you're trying to cross the road, and pedestrian comes from nowhere, and there's no algorithm that's already written in it. It is something that the AI needs to understand the surroundings and be able to pick up, the kind of environment and understand the situation and take an appropriate action instantly, rather than trying to go through the rule-based system, which was built in 80s, which is very complex. Plus, it will not address any of or all of the scenarios that happen at runtime, which cannot be planned for, because every scenario that you get, you can't plan everything. It's something that happens at the runtime. So you need to be in a place to be able to address that. So that's why the data scientists and machine learning engineers have advanced their techniques from 80s to 90s, and they started introducing some very high precision and deep learning techniques starting from 1990s. So then there's a whole lot of new era of machine learning frameworks that evolved, like Bayesian frameworks and Bayesian statistics, and several other types of neural networks, so that you're not going to have to always go on a rule-based system, rather see the scenario and see the system. And again, each algorithm is applicable for a type of system, and it's not like you can go and implement the same type of algorithm for all systems. So every algorithm addresses there's a binary outcome, for example, for logistic regression. So any binary outcome, so you can implement through, if you want to know if the email you have received is spam or not, then you're going to simply be able to implement an algorithm and come to an understanding of how exactly we can implement that. So those are the type of applications. When you are looking for binary outcomes, you implement something. You're understanding the patterns of information, and you want to cluster the information and get some classic outcomes from it, then you're going to go for some other type of algorithm. So every algorithm addresses particular situation and a scenario that you can actually leverage to implement for your neural networks. Okay, so again, so that's what we are talking about here. So ever since that the neural networks were implemented in 1990, the number of algorithms that have evolved were very enormous in terms of how exactly they're able to implement these algorithms and be able to kind of go through all the particular types of frameworks that we have. And again, this is applicable for either your speech recognition or for natural language processing, or it is just simply trying to implement for any stochastic systems where it is applicable, whether it's a quantum field for quantum computing, or whether it's physics, or it's a chemistry, any field that you can implement. And there are a lot of industries already have been successful applying these machine learning algorithms successfully. So the advent of the neural networks in the early 1990s have paved the way and the path for building the systems where you are able to build the AI systems with feed-forward neural networks. Feed-forward neural networks are something similar to what you see here. So you have an input layer and you have a few hidden layers, and then you're going to get your outcome in the output layer, which will be a result from processing the information from the input layer, connecting to all the hidden layers and producing the output to the output layer. So again, so in 90s, as we see, there are simple neural networks like this. They were not like, deep neural networks, which is what we have received from 2000s onward, that we have started seeing, even as early as 2010s, if you will, is when we started seeing, the deep neural networks. And if you read a paper from, Jeffrey Hinton, then you will understand, how the deep neural networks have evolved, and how is that more efficient in terms of training the neural network, either it's for speech recognition or for quantum computing or any other field, or even applying for reinforcement learning, how it is efficient in terms of implementing that for your particular field. And again, there's no restriction to industries. You can go for retail, life sciences, utilities, energy, so on and so forth. There's a whole number of systems that you can leverage in terms of how you're going to be able to implement this for all of your systems, for all of your industries. All right. So again, telecommunications or utilities, any industry, and all industries have been successful in implementing it. And again, you can take a look at how these types of algorithms have been implemented in the book to see how it addresses your need for your industry. And again, if you're on a journey, embarking upon a journey onto machine learning data science, and again, you will find a whole lot of prerequisites and examples and samples of implementation of these algorithms with a whole conceptual understanding of linear algebra and calculus and statistics, and then again implementations of it with formulas and actual snippets of implementation that you will find, which will help you to advance as a data scientist or machine learning engineer, and so that you can continue to pick up some new techniques that are on the horizon as we go forward into the future. So it's very important that you understand how it works in terms of, for example, we're saying that the deep neural networks have thousands of processing nodes with millions of neurons and thousands of layers that you have, so that you can process it just like brain, you have an input and then the brain processes it through multiple neurons, activates it, and then you will get, okay, here is your outcome, and then you are able to process that information, and and then you're able to come to a conclusion. Okay, here is what how I'm going to react to that situation. So maybe it's crossing a road, or it's about your choices for anything that you want to progress upon. So you can make those choices for that, and that will help you to similarly, the architecture of the neural networks is completely contingent upon the way that it's mimicking the human brain in terms of how exactly you're going to be able to implement these algorithms. So that is how it will help you to implement these machine learning algorithms. So again, though, so as I explained, there are several stages for this. You're going to receive your input information through the input layer, then it's going to get processed from the input layer, and then it goes through each connecting node and process that information, sends it to each node, and each node will contain some of the information, and then you're going to sum it up, and then you process it through the further layers of neural networks. And there is a summation that occurs, and each neuron is having a weightage that's assigned to it. So the weightage is going to get computed, and it's a feed-forward neural network. There's only a single direction it's going to go into. That will be the forward direction, and so that's when you get your output, and then you go to the threshold of the neuron, and based on that, summation happens, and then you can go forward with that. So before we start further, we're just going to take a brief pause to see if there are any questions or anything you guys have here, or I cannot say anything right now. But anyway, we'll come to the questions after the sessions to see if we can answer any of those. And again, so we're going to now take it to a little bit of advanced level of neural network to understand, to see how this neural network structure is, the architecture is. So as we can see here, we have input neurons, which we are calling A1 and A2, and then we have a hidden layer here, which is containing the neurons Y1 and Y2, and then you're going to have output here, which is Z1 and Z2. So for each of these neuron, as I said, it connects through a node. So the neuron connects to a node to another neuron, and you're going to be able to be connecting through this with a weight, and then there is a summation that occurs between these weights, and then that will give you, and then we are also creating few bias neurons here. So these bias neurons will give you additional computation in terms of how exactly we're going to be able to implement that. Again, as I said, that the genesis of deep learning has evolved from the neural networks, and again, then there's a whole generation of neural networks that were implemented, such as convolutional neural networks and recurrent neural networks and deep belief neural networks, Boltzmann machines. So there's several types of neural networks that evolved from the fundamental basic neural networks started in the 90s all the way through the 2000s and the 2010s is where we actually have several types of evolution of neural networks. Again, all of them were initially basic neural networks. So we call it basic because they were not having like thousands of layers where you can process your information. It was more of a few layers that you had, and then you can process this information properly in terms of how exactly you're going to apply it. But again, as we said here, so you can apply this for several fields. You can apply this for neural machine translation, which is for natural language processing, and machine vision. Machine vision is especially, we spoke about reinforcement learning techniques. So reinforcement learning happens completely at runtime. It's not a plan that you can have where you are expecting some outcomes to be encoded with millions of rules that you cannot implement. For reinforcement learning, happens on the fly, and as and when you encounter a particular object or anything, then you'll be able to understand how to react for that, and whether you need to seeing that impediment, you want to move away from that object, or you want to kind of get closer to that object. So that's when you can create those choices for yourself or for the AI to be able to call those shots. Just like human reacts, human is not having a preconceived notion. If a pedestrian crosses the road, how exactly you want to get around the situation is something you are going to be able to come to a conclusion on the fly at the crossroads. It's not something you plan ahead. Okay, I'm going to get a pedestrian at some time, and this is how I'm going to go around. No, because you don't know that there's a guy who's going to come up front toward you, who's causing this situation. So That's why it's important that you will implement reinforcement learning that will perform this type of, the so-called object detection methods that will tell you exactly how we are moving around the territory of the roads, and with the help of geographical system positioning systems, and it will tell you exactly what's on the horizon for you to make those kind of choices. So again, the way that again all of this information is processed through the recurrent neural networks, and there's a whole lot of set of algorithms for reinforcement learning itself, which is outside the scope of simple supervised and unsupervised machine learning algorithms we have as part of the regular machine learning and deep learning techniques that you have. Again, reinforcement learning contains its own number of algorithms. There's a deep Q learning, there's a Q learning, and there is a HER algorithm, and so there is a whole list of reinforcement learning algorithms itself. Again, we're going to go through reinforcement learning algorithms in another session, but for today, we're going to look at how the way the gradients function, especially the stochastic gradient descent. And again, as we see that how the recurrent neural networks can actually identify the signals to identify the speech patterns, and again, also there's another type of neural networks called autoencoders, and you can apply these autoencoders and stack of autoencoders onto genomics with several deep learning models, which will help you to kind of discover the new drugs and understand the sort of the causes for the diseases, so you know how exactly you're going to be able to identify. So a lot of industries have been successful in implementing this of algorithms, not just in the US but across the world. They have been successful in implementing this, and so a lot of companies in the US are on the complete industrial revolution of implementing, because reinforcement learning can also implement the robotics for conveying the belts inside the industry, where you're transferring your industrial equipment from a warehouse to another warehouse. So robotics can take such choices with reinforcement learning, and based on the deep Q learning, reinforcement learning, they can actually be able to there is a set of policy gradients that you create, and then you actually assign the rewards for computation of each of the situation. Also, if you're looking at supply chain industries also can implement the such implementations of reinforcement learning, where the demand and supply situation is inside a SCM industry is kind of very sporadic. It's not like something where you have a clear indication of the signal coming up. So there are techniques in reinforcement learning that you can implement for SCM industry as well. So you're able to understand how you can compute the demand and supply situation, so you can get the outcome computed, and then you can project, okay, this is my stock that you want to procure for your inventory management in the future for the next 18 months, for example. You want to procure some stock and you want to keep it, and then you'll be able to, because the reinforcement learning will tell you how much is the supply you have and how much is the demand in the industry, and then you will be able to fulfill your inventory based on those situations. So yeah, industries have been successful in implementing reinforcement learning even for supply chain management as well. So again, as I said, there are a few other techniques of neural networks, such as restricted Boltzmann machines and deep belief neural nets. So these are all, because these have been implemented to overcome the performance issues that we have with earlier neural network, evolutionary neural networks. So these were implemented to overcome those issues and come up with an approach that will help them to, overcome that, and come up with an implementation which will help you to overcome those challenges of performance. So that's what it is. And again, if you see a verbose paper some time ago, many years ago, he clearly stated that it's very important that you will have implementation of gradients in neural network that will help you to especially feed forward neural networks to compute the forward propagation and back propagation, which is what we're going to take a look at shortly from now. And we're also going to examine closely the prerequisites and the math behind this feed forward neural networks with stochastic gradient descent and the back prop and forward prop. That will tell you the automatic differentiation in terms of how exactly you're going to be able to implement that. Now we're going to take let's take a sort of a deeper dive into the mechanics of the back propagation to see, again, there are a lot of libraries that are being provided for us. For example, if you're going to implement auto differentiation, or you're going to implement some sort of calculus chain rules. There are some modules that you can leverage and packages libraries you can implement from PyTorch, Python, and TensorFlow. Again, PyTorch and TensorFlow mostly because if you're looking at Python, it's mostly like it's a bare neural networks by NumPy. You have to calculate everything with a package called NumPy. You come up with all of your calculations. There's not much of a support from the packages that will help you to even activate a neuron. So you'll have to create everything on your own. But coming to PyTorch and TensorFlow, the recent neural networks, which were released sometime in 2015 and 2016, the modern programming languages like PyTorch and TensorFlow can actually help you to implement without having to manually perform a lot of computations on your system. That will help you to implement without such complications. And again, we're going to take a look at back propagation algorithm, as we said, for the stochastic gradient descent. And so this is how we're going to compute. You guys already have taken a look at the architecture of this neural network. And this neural network we are seeing here is primarily having a couple of neurons. And each, as you see, that we're going to initialize these neurons with some randomly assigned weights. It's important that you randomly assign the weights. And I'm going to assign it with some specific value in your mind that's going to actually create some bias in it. So you want to apply initially randomize this value so that here you get is the weights have been randomized and applied to the neural network so that each neuron is assigned with a particular weight. And so the A1 and A2 are your input neurons, Y1, Y2 are the hidden neurons, and Z1, Z2 are your output neurons. So here we are assigning a lot of weights like weight 1, weight 2, so on and so forth. So this weight is going to tell you what is exactly the weight the neuron carries in terms of summation of the value in it. So again, it's why we are initializing these neurons and the neural networks and assigning these values is because you want to compute your total output values without any room for bias in that case, and that's why you are performing that. So let's take a forward pass on this neural network, and we're going to apply and activate each neuron. And again, as I said earlier, there is a there's a way of actually implementing this neural networks by activating each neuron. Again, after this session, I'm going to share you a link of a blog that I created, how actually you're going to be able to activate each of these neurons. There are several ways for activating these neurons. Like, for example, there's a sigmoid function, there's a logistic function, and there is a ReLU, rectified linear unit. And so those are like several types of activation functions available for you to understand and implement. I'm going to share my blog so that you can see how you can actually implement on any of your programming. So I provided samples for Python, PyTorch, and TensorFlow, so you can try to implement it. But for this session, let's see that how we're going to actually be able to, because it's very important before you get into the programming language, you actually manually compute this on a piece of paper, just like this, and then you get your calculations right, and then you go and program it, and then you calculate it, and then you see how the program computes it. But if you're not having an understanding how to compute it on a paper, then it's going to be complicated for you to actually implement with the program itself. That's why I'm giving you a manual computation just on the piece of paper that you can work on, and then you can actually compute this, and then you will be able to implement this. So here, in order to compute the net input y1, right? So we are transferring this information from a1 to y1. So for that, we need to calculate the weight 1 multiplied by a1. Then you sum it up with weight 2 and multiply that with a2, and also take consideration of the weighted the bias node we created, and multiply the bias 1 with weight with the 1, which is what is the value we assign it to it. That will give you the y1. So if you put this into numbers, if you compute it, that's the net input y1. So we're simply multiplying this. Similarly, in order to get your hidden layer neuron computed y2, you're going to again take the weight of each neuron, and then you're going to start computing it with weight 3 multiplied by a1 plus weight 4 multiplied by a2 plus take also the bias 1 plus multiplied by 1. That will give you the net input of the y2. So we calculated so far the net input of y1 and the net input of y2. So now, as we said that we just computed this, but now the neuron has to be active for it to function. To be able to produce an outcome, the neuron has to be active. So we're going to apply a logistic function as an activation function. So again, as I said, the logistic function is a scaled function of a sigmoid function. Again, what is a logistic function? What is a sigmoid function? What is a ReLU function? So on and so forth, right? So for all of this, I'm going to share a blog so you can understand how do you actually implement logistic functions and how do you activate them for each neuron with an example. So that will give you the understanding. So we're not going to go through how exactly you're going to apply the logistic function here, but you're going to get information for you can go through that. So now we have computed that both A1 and A2 by applying the logistic function and activation function. And these are the values you have received. And again, it's also, we saw that there is an output layer we are creating here called with the neurons called Z1 and Z2. So the net input for the Z1 and Z2, we're going to compute here. For example, start with the net input Z2, net input of a Z2. Then we take the weight 7, multiply with the net output A1. Then we sum that up with W8, multiply with net output A2. Then take the bias 2 node now and multiply with the assigned value of the weight in it. And then here is the, the logistic function I just spoke about is 1 plus e to the power of net Z2. This is a logistic function we're going to compute now so that we know exactly what is the net output of a Z2. So we already have computed all the inputs. Now, in order for it to compute the output, you're going to apply a logistic function, a simple logistic function. And that will tell you, exactly what is the net output of Z2. So here we apply this with the scale sigma function. And so when we apply that, this is what you're getting as your net value. So whatever the net input that you have received in the earlier case, you're going to take that and you're going to apply that to the e power of -1, the entire net input, and then you get an exponential of that, and then that will give you that net output. So then you have the net output now. So again, every time you compute these values for the backdrop in your algorithm, you'll also get into some errors that you can have because you're calculating so many. And again, this is a simple neural network. Think about thousands of neural networks and thousands of hidden layers inside of a neural network, and there is a room for error that you could have whenever you're transferring the information from neuron A to neuron B. So we're going to take a look at how do we avoid this type of errors, and how do we compute errors, and how can we further not have these errors, or how do we have a handle on these errors. So let's first calculate the error and see how we can reduce this margin of error that we're going to have. So you want to compute the total error is basically you're going to apply this formula, sigma of 1/2 ideal target minus actual output squared. So ideal target is either a Z1 for your, to compute the error of Z1, and you're going to compute the output error Z2, and then you're going to simply subtract that from your net output that we just computed for Z2. Similarly, We're going to compute for Z1, and we're going to compute the error here. So for the error that you have received is if you're going to take the net output of Z1 and Z2, which we calculated earlier, substitute here, and this is exactly the error that you're getting in terms of Z1, the output neuron Z1. And again, you're also having error Z2, and that's the error you're having in the Z2. And the total error is basically however many neurons you have. So for example, in this case, you're having Z1 and Z2. So you could have a whole lot of number of neurons in Z1 onwards to Z99, for example. So how you're going to have implementation is you're going to simply accumulate all these neurons errors computed individually, and you sum it up, and that will give you the total error that you have in the neural network. So you know exactly, the error, the margin of error is, this is the margin of error, 0.2983711109. And so that's when you are able to actually be able to have the impact of the rate of change in weight 5 contributes to the total error. So we also are going to calculate sort of the partial derivative of the error total, and that you can represent total by the weight 5. So again, as I told you, the way that we're going to implement the backprop of a stochastic gradient descent is with a chain rule. So chain rule is, again, what is a chain rule? You can refer my book. I will give you a fundamentals of calculus of all the equations of calculus, and then again, what is a chain rule, and then how exactly I'm going to differentiate a function of a function. So a chain rule is applied to differentiate a function of a function. So basically here we are trying to find the cosine value of z squared. So what we are going to try to find it is basically we're going to determine the function of a function. So that would be, let's consider two functions here, f of z and z of z. And so the function of a function x is basically f of z of z. So z of z is a function, and you're computing the f of z of z, the function of the entire z of z function. So a g here is a square function, and f here is a cosine function. So mathematically, if you want to represent it, you can represent it this way. So because we're trying to find the cosine of z, so f of z is basically cosine of a z of z, which is a z square, and the function of z is fz square, which is a cosine z. And when you apply that, so basically what happens is you're finding the cosine of z, which is a cosine z square. So if you want to differentiate this, then you're going to have to find the partial derivative of this. So the partial derivative of this d of x by dz. And if you want to consider the substitute as y as z of z, then you can apply this chain rule as basically d of x by d of z is simply d of x by dy multiplied by dy by dz. That is the chain rule. So that's how you're going to compute your partial derivative of dx by dz to the chain rule with a differentiation of a function. Now that we performed, we simply applied a forward pass just now. We're going to take a look at backward pass. And again, you're going to represent with the total error by the weight 5. And now if you're going to apply this same chain rule we spoke about to a backward pass, you're going to simply apply this total by weight 5, and then you're going to apply this for the whatever the output we got from the Z1. So you're going to simply divide the error total by the Z1, multiplied by the output of Z1 by the net output of Z1, and net output of Z1 by weight 5. So this is how you're going to compute it, and your ideal target, which is the Z1 minus output of Z1 whole square plus 1 by 2 of our target, it is Z2 minus output of Z2 whole square. So we put the values into it based on our earlier computation into it. So you're going to simply reduce the room of error, and then that's what you're going to get here as your total computation value that you received here. So that is in a nutshell of how exactly you're going to be able to basically apply this. And again, if you're going to take a look at the other way of implementing this, so this is the function I was talking to you about earlier. So where you can actually take a look at the activation functions. So each activation function, how you're going to apply the logistic activation function, or how exactly going to be able to apply your hyperbolic tangent function or tan activation function, or you want to apply the ReLU, which is a rectified linear unit activation function. So you can take a look at each of these functions and see how you can implement. Again, there is an example for you based on your PyTorch, TensorFlow, or Python. You can implement that. So that'll give you the value of that. And again, so if we go through this, okay, so yeah, I'll come back to that. So, but anyway, the code is available. I was just trying to run the code, but the code is already here, so you can run it yourself in this blog, and so you'll be able to implement that on your own. So now we'll come to any questions that you may have in this. Um, so, yeah, if you have any questions, please feel free to come up with the questions. Any questions from you on this topic? You guys have any questions? Yeah, you can always send your questions through LinkedIn. If you have any questions on a particular topic or any clarification on any pending topic, feel free to send a question and I'll be able to answer you for, for any topic in this or any other area that you want to. If you're on a research and you're performing a lot of research, then you run into some issues also. Feel free to come back with any questions from your topic. Not hearing any questions, so you guys are still here?
Hi there. Have you finished now?
Yeah, I was just wondering if they have any questions on the topic. Are there any questions on any of the topics? You require any information here? Here is a blog that you can utilize. So that is the blog where you can find whatever that we spoke about, activating the neuron and implementation of activation of a neuron. You can find that code in there. You can find the book, or you can find in this article. Both cases, you can find that information. Yes. Yeah, I'm just wondering if there are any questions, but I shared a blog in case they want to go ahead and run the blog. That's the blog for them. Thank you very much.